Hi! In today's lecture, we're going to construct the molecular orbital diagram of hydrogen fluoride. Let's begin. For the hydrogen fluoride molecule, we have a total of 8 valence electrons, 1 coming from the hydrogen atom and 7 coming from the fluorine atom. For the orbital energies, we have the lone orbital for the hydrogen, which is the 1s, at negative 13.6 electron volts, and the valence orbitals for fluorine would be 2s at negative 40.17 electron volts and 2p at negative 18.65 electron volts. Symmetry-wise, the hydrogen atom only has the 1s orbital, whereas the fluorine atom has the 2s and the 2p orbital. So you expect interactions with respect to symmetry between the 1s of hydrogen and 2s of fluorine. You can also expect an interaction between 1s of hydrogen and a 2p orbital of fluorine. Considering both the orbital energy and the orbital symmetry, there is only one possible overlap between the hydrogen and the fluorine AOs. And this is the hydrogen 1s and the fluorine 2p. You can see that the hydrogen 1s energy level is negative 13.6 eV and the 2p of fluorine is negative 18.65. However, for the hydrogen 1s and fluorine 2s, the orbital energy difference is quite high, therefore there is no significant interaction between the two. I have here a partial MO for the hydrogen fluoride molecule. So you can see that the 2s orbital of fluorine is at the lowest position because it's at negative 40, whereas the hydrogen 1s is at the highest position at negative 13.6. You have 1 valence electron for the hydrogen atom and you have 7 valence electrons for the fluorine atom. And we already know that there will be a significant overlap between the 1s and one of the 2p orbitals of fluorine. So it will look like this. We have the blue lines corresponding to the generated MO from the overlap of the 1s and one of the 2p orbitals of fluorine. And then you have the other orbitals here and here which did not interact with any other orbital. And you can see as well that their energies did not change upon creating the MO. So you have here the labels. This one is sigma. This one is also a sigma. This is a pi. And this is a sigma star. It's easy to visualize that there is a sigma overlap between the 1s and one of the 2p orbitals of fluorine. However, for the non-participating molecular orbitals, there are still sigma and pi labels. And we need to go back to our definition of the pi and the sigma bond. So here is a visual representation of this orbital here. As you can see, it did not interact with any other orbital from the hydrogen, and yet it is something like this. We cannot ignore that there is a bond created between the hydrogen atom and the fluorine atom, and the electron density will be distributed to the whole molecule in accordance to the postulates of the molecular orbital theory. These orbitals here are essentially p orbitals, and they are labeled as pi because there is a nodal plane. When we populate these orbitals, we have 8 electrons to be distributed. 1, 2, 3, 4, 5, 6, 7, 8. And here are some of the key takeaways. These 2 orbitals here and this orbital here did not participate in an orbital overlap. And these are called non-bonding molecular orbitals. You can see that a feature of a non-bonding orbital is that it retains the energy value of the originating atomic orbitals. The bond order is equal to 1, and this is calculated using the formula. We have 1/2 times the number of electrons in the bonding MO. We have 2. This 2 and this 4 are electrons in the non-bonding molecular orbital. So they are not included in the formula for bond order. There is no electron in the sigma star orbital. So that gives you a bond order equal to 1. Meaning, in the hydrogen fluoride molecule, there is a single bond between hydrogen and fluorine, which is consistent to its lowest structure. Another takeaway is the prediction of the polarity of the HF bond. You know that HF is a polar molecule with the electron density more concentrated on the fluorine atom. You can see here that the electrons are occupying an orbital that is closer in energy to the atomic orbital of fluorine rather than the atomic orbital of hydrogen. You can say that this sigma bonding orbital has more fluorine character than hydrogen character, which justifies that these electrons are more concentrated on fluorine. Some references account for the presence of these 4 plus 2, 6 electrons in the molecular orbital of HF as lone pairs in the lowest structure of the molecule, mainly because these 3 orbitals have the same energy as the fluorine AOs, making these orbitals purely fluorine in character, which is the same with its lowest structure.